morning, friends. After the discussion of the efficiency of the Carnot engine, we are going to discuss about the Carnot theorem. What is the Carnot theorem? Already we discussed about the efficiency of a Carnot engine. So N is equal to 1 minus T2 upon T1. T2 is the temperature of the heat sink and T1 is the temperature of a heat source. That means the Carnot cycle takes place in a Carnot engine is operated between the two temperature of the heat source and temperature of a heat sink. That means the efficiency of a Carnot engine is depends on the temperature of the heat source and heat sink. Clear this? Okay. Now, what is the Carnot theorem? We have to discuss or obtain the Carnot theorem. So Carnot theorem is divided into two parts. That is the discussion on the base of second law of thermodynamics. Already we discussed the two statements of second law of thermodynamics, Kelvin-Planck statement and also Clausius statement. Now Carnot theorem is divided into two parts. Part 1, no engine can have more efficiency than the reversible engine operating between the temperature T1 and temperature T2 of hot source and also the cold sink. That means, what is the statement? No engine can have the more efficiency than the reversible engine operating between the two temperatures T1 and T2 of hot and cold reservoir. Only the Carnot engine has the maximum efficiency. No any engine has the more efficiency than the Carnot engine. This engine is reversible and operating between the two temperatures T1 and T2. T1 is the temperature of the hot and T2 is the temperature of the cold reservoir. Right? And second is that the efficiency of the Carnot engine is independent of the nature of the working substance. So these two parts represents the Carnot theorem. Again, the Carnot theorem is divided into two parts. One is, no engine can have more efficiency than the reversible engine operating between the two temperatures T1 and T2 of hot and cold reservoir. So this statement says that the efficiency of a reversible engine is always maximum compared to the other engine. This engine operating between the two temperature of the hot source and temperature of a cold sink. Now second, the efficiency of a Carnot engine is independent of the nature of the working substance. Whatever the working substance filled in piston cylinder arrangement, there is no depends on the efficiency or the efficiency of a reversible engine or the Carnot engine is not depends on the type of the nature filled in piston cylinder arrangement. Right? Therefore, to prove this Carnot engine, to prove the result A, consider a reversible engine R and irreversible engine I working between the same source and the sink. Here we consider the two engines. One is reversible engine R denoted by R and second is irreversible engine denoted by I. Both operating between the same temperature, that means the same source and sink. That is shown in the figure. There is the irreversible engine, there is the reversible engine. Irreversible engine absorbs the heat Q1 from the hot source and as a result the work done by the gas and Q2 is equal to Q1 minus W, amount of the heat is released in heat sink. While the reversible engine, it absorbs the Q2 amount of the heat, Q2 is equal to Q1 minus W. Q1 is released and W is the work done on the gas to absorb the Q2 amount of the heat. Here in reversible engine, the work done on the gas to absorb the Q2 amount of the heat. Therefore, Q2 minus W heat is released as Q1 in a heat source. Now we are going to discuss about this diagram. It's shown in figure. I act as a heat engine and I act as a refrigerator. Already we discussed the working of the heat engine and also the refrigerator. We derive the equation of efficiency of a heat engine 1 minus Q2 upon Q1, and also we discuss and derive the equation of the coefficient of performance for refrigerator. Now, suppose the irreversible engine absorbs the heat Q1 from the source and work done by the gas. Therefore, gas is expanded and Q2 amount of the heat is released in a heat sink. Again, the I acts as a heat engine. It absorbs the Q1 amount of the heat from the heat source. So as a result, work done on a working substance and Q2 amount of the heat is released in a heat sink. Now, as when will make such that the R returns the same heat Q1. Here the arrangement of the two engines, irreversible and reversible, are arranged in such a way that whatever the heat is absorbed by the irreversible engine, the same heat is provided by the reversible engine to the heat source. And arrangement will be made such that R returns the same heat Q1 to the source, taking heat Q2 from the sink and requiring the work W is equal to Q1 minus Q2. Q1 minus Q2 to be done on it. That means reversible engine absorbs the heat Q2. To absorb this heat, the work done on the gas of the working systems, as a result, the Q1 amount of the heat is released in a heat source. How much work is required? Work required is Q1 minus Q2. And the heat given to the sink, Q2 is Q1 minus W, and the necessary work will be done. Here the reversible engine, that means the heat engine releases the heat, Q2 is equal to Q1 minus W. This heat is absorbed by the reversible engine, that means the refrigerator. To absorb this heat, the work done on the gas. So as a result, Q1 amount of the heat, only this heat is absorbed by the irreversible engine or the heat engine. That is heat again returned back to the hot source. Okay. So that is the one part. After that, we are going to discuss about on the base of the efficiency. Our statement is that no engine can have the more efficiency than the reversible engine operating between the two temperature T1 and T2. So we discuss later, again we revise it. So for that purpose, to prove the result A is that no engine can have the more efficiency than the reversible engine operating between the two temperature T1 and T2 of the source and sink, or the hot and cold reservoir. For that purpose, to prove this statement, consider a reversible engine R and irreversible engine I working between the same source and the sink. Let's show in the figure. Here the I act like a heat engine. It absorbs the Q1 amount of the heat from the source. So as a result, work done by the gas, and Q2 amount, Q2 is equal to Q1 minus W, amount of the work heat is released in a heat sink. Right? Now, the arrangement will made in such a way that the R, reversible engine, returns the same heat Q1 to the source. Q1 to the source. Now, taking the heat Q2 from the sink and required work W is equal to Q1 minus Q2 to be done on it. How the reversible engine again give the Q1 amount of the heat to the source. For that purpose, it absorbs the Q2 amount of the heat from the sink. To absorb the heat Q2, the work done on the gas, that means the gas is compressed. Gas is compressed. How much work done? W is equal to Q1 minus Q2 to be done on a system. And as a result, the Q1 amount of the heat is released into the hot source. The heat given to the sink Q2 is equal to Q1 minus W, and necessary work will be done. Now, as we assume that the efficiency of a reversible engine is less than Ni, we want to prove that no any engine has the more efficiency than the reversible engine. Here we consider the efficiency of a reversible engine is Nr, and efficiency of only heat engine, that is not a reversible, irreversible, as the efficiency is Nr. Initially we assume the efficiency of a heat engine or the irreversible engine is more than the efficiency of a reversible engine. Then engine R gives the less work than the engine I. Here the efficiency of I is less than the efficiency of irreversible engine. Therefore, I cannot provide the necessary amount Q1 to the source. Already this Q1 is absorbed by the heat engine. Because the efficiency of a reversible engine is less than the irreversible engine. Hence, for given Q1, the work done by the reversible engine W is less than the work done by the irreversible engine W dash. Therefore, W is less than W dash. With reacting like a, with R acting like a refrigerator. Here the I is act like a refrigerator, I is act as a heat engine. Therefore, Q2 is equal to Q1 minus W. That is greater than the Q1 minus W dash. So here the W dash is the work done by the irreversible, and W is the work done by the reversible engine. So Q1 minus W is greater than the Q1 minus W dash. Thus, the couple irreversible and reversible system can extract the heat Q1 minus W minus Q1 minus W dash is equal to W dash minus W. W dash minus W. From the whole reservoir and delivers the same amount of the work in one cycle, and that is against the Kelvin-Planck statement of the second law of thermodynamics. So if this happens, the efficiency of a reversible engine is less than the irreversible engine. So what's happened? The total amount of the heat absorbed is Q1 minus W minus Q1 minus W dash. So it's equal to W dash minus W. Therefore, from the cold reservoir and delivers the same amount of the work. The same amount of the heat is delivered to the cold reservoir, and the same amount of the work is done in one cycle, and this is against the Kelvin-Planck's Kelvin-Planck statement of second law of thermodynamics. Kelvin-Planck's statement is that no any heat engine can convert the 100% of the heat absorbed into the mechanical work. Right? Therefore, hence the Ni, our assumption is low. Therefore, the efficiency of a irreversible engine is greater than the efficiency of a reversible engine. Hence, the Ni is greater than Nr is low. It means the efficiency of a reversible engine is always greater than the efficiency of irreversible heat engine. Now, the low engine can have the efficiency greater than that of the Carnot engine. The maximum efficiency of a Carnot engine N is equal to 1 minus T2 upon T1 is independent of nature of the system. Here the efficiency is only operate between the two temperature T1 and T2, that means the temperature of the source and temperature of the sink. That is not depends on type of the nature of the working substance. So that an ideal gas is taken as a working substance in Carnot engine. Therefore, the efficiency N is equal to 1 minus T2 upon T1, and another equation N is equal to 1 minus Q2 upon Q1. Therefore, Q2 upon Q1 is equal to T2 upon T1, or Q1 upon Q2 is equal to T1 upon T2. So that is our second statement. The efficiency of a Carnot engine is independent of nature of the working substance. Clear this? So that is our Carnot theorem. Here we prove the both statement. One statement is that no any engine has the more efficiency than the reversible engine operating between the two temperature T1 and T2 of hot and cold reservoir. And second part of a Carnot theorem is that the efficiency of a Carnot engine is independent of nature of a working substance. Clear? Again, we revise the first statement to prove the first statement or the first part. Here we consider a reversible engine R and irreversible engine I working between the same source and sink. There is the irreversible engine, there is the reversible engine. Okay. As shown in figure, I act as a heat engine and R act as a refrigerator. Suppose the I absorb the Q1 amount of the heat from the source. As a result, work done by the gas, and Q2 is equal to Q1 minus W. Amount of the heat is released to a sink. Now, the arrangement will made in such a way that the R reversible engine returns the same heat Q1 to the source, taking the heat Q2 from the sink, and required work W is equal to Q1 minus Q2 to be delivered on it. That means the R returns the same amount of the heat Q1 to the source, taking Q2 is equal to Q1 minus W amount of the heat from the sink, and to absorb this heat, the work done on a system is this Q1 minus Q2. Heat given to a sink is Q2 is equal to Q1 minus W. The necessary work will be done. To prove this part A, we assume that suppose the NR is less than NI. That means the efficiency of a reversible heat engine is less than the efficiency of a simple heat engine. Then engine R gives the less work than the engine I. Therefore, the work done by the reversible engine W is less than the work done by the irreversible engine W dash. Now, with R acting as a refrigerator, therefore Q2 is equal to Q1 minus W, that is greater than Q1 minus W dash. Q1 minus W dash. Therefore, thus the couple I and R system, that means the system of irreversible and reversible engine, extract the heat Q1 minus W minus Q1 minus W dash is equal to W dash minus W from the cold reservoir, and delivers the same amount of the work in the cycle. So both operating at both deliver the same amount of the heat to the cold reservoir, and same work is done in one cycle. So this is the against the Kelvin-Planck statement of second law of thermodynamics. Therefore, our assumption is NI is greater than NR is low. Means no engine can have the efficiencies more than the Carnot engine or the reversible engine. Right? Now we are going to discuss the second part. The efficiency of a Carnot engine is independent of the nature of a substance or the working substance. The maximum efficiency of a Carnot engine N is equal to 1 minus T2 upon T1 is only depends on temperature of the sink and temperature of the source. It is independent of the type of the nature. Therefore, efficiency N is equal to 1 minus T2 upon T1 and efficiency of heat engine N is equal to 1 minus Q2 upon Q1. Comparing these two equations, we obtain T2 upon T1 is equal to Q2 upon Q1. Therefore, T1 upon T2 is equal to Q1 upon Q2. That is the independent of nature of a working substance. So hence that is the Carnot theorem. Right? We have to prove these two parts of the Carnot theorem. Efficiency of any heat engine is never more than the efficiency of a reversible or the Carnot engine. And second is that the efficiency of a Carnot engine is independent of type of working substance. Clear?